Hello, today's lesson is on 3.5 on a concept called work. So we're going to start by looking at these pictures and deciding which person is doing more work and why we might think so. So here's the first picture. This lady looks very happy lifting her weights. And then this gentleman looks like he's in complete agony. Which person do you think is doing more work? Usually if we were in class, I'd get a whole bunch of answers, some sarcastic, some not, of this guy here doing more work, or just being more dramatic, perhaps. But what in the picture shows you that he is doing more work? It's the fact that he's lifting a heavier mass. So this guy is doing more work because he has more mass to lift. Next picture. Okay, first guy probably did a deadlift, so he lifted that weight from the floor to hip height. The other lady was probably doing clean and jerk, maybe, where she lifted that weight all the way overhead from the ground. So who's doing more work here? She is. Looks like she's at the 2004 Olympics in Athens, probably lifting a really big amount of mass. But the thing I want to point out here, the reason why she's doing more work, in addition to more mass, is that she lifted it a larger distance. That's why she's doing more work in the physics sense of the word work. Last example. Weightlifter on the moon or a weightlifter on the earth. We studied gravity. We all know that gravity on the moon is far less than it is on Earth because the moon has a smaller mass than Earth. So where would you be doing work? Where would it be harder to pick something up? On the moon or on Earth? Harder to pick something up where gravity is more. So the work is happening here because of the larger force due to gravity. All right, let's take a look at the physics definition of what work is. Science 10, we learned that work is the change in energy. Remember that this little triangle symbol is the Greek letter delta, and it stands for change in. But really, that's a very simplified way of saying something much more complex. So on the last slide, we did figure out that work was proportional to mass, it was proportional to distance, and it was proportional to acceleration. That's all this little symbol means, is proportionality. So if I was to put these two together, mass and acceleration, there's something that we've already studied that takes into account mass and acceleration. Newton's second law, F equals ma, force. So the force applied is going to be proportional to the work done, as well as the distance. Put those together, you get this formula. From your formula sheet, work is force times distance. Do a quick substitution of F equals ma, and you get work equals ma times distance, or displacement, I should be saying. These are two very useful formulas. Very simple, as you can see. There's not much complexity here. That's why we call the first unit death equations, and everything else is quite easy after that. But something that you should notice here is if you look at work, it does not have a vector arrow on top of it because work is a scalar. When we talk about the work an object is doing, it's only the magnitude that matters. Direction doesn't matter. However, if you look at that equation again, force and displacement both had vector arrows. So their direction does matter. This is very, very important. This is really the only thing I need you to take away from this lesson. Force and direction must be, or pardon me, force and displacement must be in the same direction for work to have been done. So, where we might use the word work in the English language differently, when we use it in physics, we're talking not about how hard something might be, because lifting a weight or carrying something heavy might be really hard, but we might not be doing any work at all. And I'll show you an example of that in a second. But force and displacement must be in the same direction for work to have been done. The first example, a rocket taking off. The force of the jet fuel being propelled out of the back of the rocket is forwards. That's how we're sending the rocket straight into the sky. And the displacement also forwards, hopefully, or else we have a crash on our hands. But in this case, force, displacement, both pointing in the same direction, so we can say work is done in this situation. This guy is carrying a box, and I would show you this in class with my hands just on the bottom of a box. So what way am I applying force to the box? The box is being pushed. If my hands are on the very bottom, I'm holding it up by applying a force up to the box. But as I walk across the room, you can see that those two are not in the same direction. So although you might work up quite a sweat if you're maybe moving and you're carrying a lot of really heavy boxes around, but you're not actually doing any work at all when you just hold a box and walk across a room, because force and displacement are not in the same direction. The moment when you did work in this situation would be when you lifted the box from the ground to your hands, because the force was up and the box moved up. That is work. But if you're holding it up and you're moving sideways, you are not actually doing any work at all. So this is where we have to get out of our own heads. We can't think of work in the everyday sense of the word, where it might be something hard that's hard to do. We have to think of work as being force and displacement in the same direction. You have to always tie it back to that equation that we developed. Oh, I better erase the answer here before we do the question. Okay, we have how much work is done lifting a 25 kilogram box to a height of 5 meters. Why don't you pause the video and list all of your variables, pick your equation, and see if you can sub your numbers in. Here's my solution. Question gave me a mass of 25 kilograms. It also gave me a height of 5 meters, that I'm lifting something. I could say height, but I could also say displacement. The object has moved 5 meters. There's another thing that I know automatically. If I'm lifting something up in the air, the acceleration that it's facing is negative 9.81 meters per second squared. Now, we've got work that we're looking for, which usually comes on the formula sheet as force times displacement. And some of your formulas might put absolute value bars around those. So if you remember from Math 20-1, absolute value bars just make any number positive. Because work is a scalar, if you have any negatives that don't cancel out at the end, just get rid of them. Work shouldn't have positives or negatives on it. It shouldn't have a direction. It's just a magnitude. I don't have force though, but I do have what force is equal to. By Newton's second law, it's equal to mass times acceleration. Pop my numbers in. And I'm leaving the negative just out of habit, but really, I'm not going to write it in my final answer. You can just think of this in absolute value bars. And I get 1.2 times 10 to the 3. Now, I don't know what the units are. I could figure out the fundamental units because I know that I just multiplied together kilograms, meters per second squared, and meters. Remember, these are over 1, and multiplying fractions, you go top times top, bottom times bottom. These are the units that I just got, but you know that scientists can be quite lazy. We also like to give credit where credit is due, so we actually use the unit joules, named after some famous old dead guy who probably discovered a lot about work. And what is a joule equal to? It's equal to a kilogram meter squared per second squared. How much work is needed after lifting the box to carry it horizontally 250 meters? The 250 meters is what we call a distractor. It's there so that you start making a list of variables instead of thinking. So students who are successful in physics always have to think about the theory behind things. If you're just getting ready to do math and follow the formulas, you're not quite digging into the concepts of physics. So how much work is needed if you've got that box lifted already and you're just going to carry it horizontally? Well, force and direction, like we just saw, are in opposite directions. Force is up and displacement is across the room, or 250 meters east, maybe, something like that. So the work needed to just hold something and not move it in the same direction as the force that you're applying is 0. 0 joules. OJ. Let's talk the physics though. The whole point of physics is being able to explain why something is the way it is. So it's 0 joules because force and displacement are in different directions. Okay, what about this guy? We've got an applied force. He's kind of pushing down on an angle on this box to move it. And he's moving it horizontally. So is there work being done? Yes and no, so sort of. Since we can break any vectors down into the x and y components like we did in the first unit, yes, this guy is doing work in the horizontal direction because this red vector, this is the force that he's applying as a horizontal component, matches up with the direction that the box is moving. So these two vectors here combine to give us work. Now, the applied force is down here on the hypotenuse. So he is applying a force on an angle, but part of the force is going directly into the floor, and that's obviously not the way the box is moving. So that blue vector there does not contribute whatsoever to the physics definition of work. Here's another formula on your formula sheet. We're going to use this in the next example where a force is applied on an angle so that we can get the work just in the horizontal direction. So here's the scenario. Ryan is shoveling the walk. He's applying a force of 150 newtons down the shovel handle. And those of you who do any shoveling know that you usually put the shovel on an angle when you shovel. The applied force is 150 newtons. Now that force breaks up into an x component and a y, a horizontal and a vertical. It says there's a 35-degree angle between the shovel handle and the horizontal line, and he ends up going 10 meters. right? And this is vertical and horizontal. So of course your shovel moves in the horizontal direction. How much work is being done? Well, if we're moving horizontal, then the horizontal component of the applied force is the only one that contributes to work. What side of the triangle is that? Well, if here's my angle, opposite, hypotenuse, adjacent, you might be realizing why cosine was in the last formula. My adjacent side and my hypotenuse will go together to find my horizontal force. Now, the previous page shows that you've got absolute value bars around everything here. It just means that you don't need to contribute any negatives into what you're doing here. The force applied is 150 newtons. But how do I actually get the force in the horizontal? I take that and I multiply by the angle. So I'm actually breaking this up into parts here. Because these two parts that I've drawn right now, cos 35 and 150, they're exactly what we would have gotten if we just used SOHCAHTOA, 35 degrees equals adjacent over hypotenuse. If I had written it out like that, you would have multiplied the 150 over, and you would have had the horizontal component of force being 150 times cos 35. This equation just happens to put the displacement in between those two. It's just a convention of the equation, that's all it is. So I'll just put it in the middle here, but that's where those parts of the equation come from. So how far it moves is the 10 meters. Multiply them all together, and I'm getting 1.23 times 10 to the 3, and work is measured in joules. Something you'll just have to memorize. Now, this should be a pretty short and simple lesson because that's as complicated as we're going to get. Having to match the horizontal with the horizontal to get your force, that's all we're doing. And in fact, we're omitting this entire slide with more complicated angle questions. And we're actually omitting those practice problems because they do all have angles in them. And all I want you to get from this lesson is what's the formula for work? Force times distance. And what's the big physics theory behind it? Force and distance have to be applied in the same direction for there to be work. I also want you to understand that work is change in energy because that's our next lesson. And I want you to know the units for work are joules. But as far as calculations go, there's nothing I can give you here that's more complicated than Science 10 examples because we're going to just skip over the ones with angles. Let me know if you need any help with this concept or move on to lesson 3.6.